Hello judges and everyone, my name is Max Dew, and I'm a grade 9 student at Queen Elizabeth High School. Thank you for taking the time to check in on my science fair project. Before my presentation, I would like to present to you a scenario. This is Andy at home, and he has suddenly gotten cardiac arrest, and his phone has fallen out of his hand, and his pills are downstairs when he can barely even walk. So, he presses the emergency SOS button on his chest, which alerts community medical bystanders and the EMS. Now, every second counts in an out-of-hospital cardiac arrest emergency. This is because, for out-of-hospital cardiac arrest patients, the chance of survival is close to zero within the first 10 minutes. However, average EMS response times is 9 minutes in the US and Canada, and 22 minutes in rural areas. During COVID, it is even slower. Unfortunately, the vast majority of these patients have already died by the time that the EMS has arrived. Currently, community bystanders is a solution. They provide CPR in the first few minutes and help to increase the survival rates by 2 to 3 times. However, over half of cardiac arrests happen when the patient is home alone. Without EMS or bystanders witness, the survival rate is only around 4%. Who can help these patients? So, how can we solve this issue and save more people? Well, a drone flies fastly and freely. So can we use a drone and make it intelligent so it can save more people before an EMS arrives? I want to realize this crazy idea. I've defined my drone innovation in order to focus on the two most critical aspects. First, to help save more cardiac arrest patients, especially those who have gone unwitnessed at home. And second, to start intervention earlier in order to help patients reduce the neurological damage. Here are my design ideas.
The drone activates when it receives the alert from the wireless SOS button on the patient.
It can locate patients in seconds, whether they are upstairs or downstairs. The drone can enable surveillance connection with an EMS team through live video, so the first responder can quickly know the patient's situation, as well as the precise location in the house. A rapid diagnosis could also be done if the patient's profile is uploaded. The drone carries a small box of emergency medication that is pre-prescribed for that patient. This can come in forms of either pills or an inhaler, which means that when the patient needs it, it is close at hand. If the EMS team decides that the patient is in need of emergency medication, then they may enable an emergency protocol on the drone that will allow the drone to complete the emergency intramuscular autoinjection. When the emergency protocol on the drone is activated, the drone will first extend the injector. Then, the drone will inject. If it is necessary, the drone may open a door to locate the patient. First, the drone will fly up to the door and it will clamp. Then, the drone will land, providing support. Then, by using a motor, the drone will turn the doorknob. Then, the door will open. Then, the selfie stick will retract, allowing for the drone to fly into the room and locate the patient. This innovation is a mechatronics product innovation, and for the past 3 months, I've used various methods to design this and build this from scratch. By using conceptual design, engineering analysis, calculations, computer science, testing, and retesting, I have developed this drone. To complete the door opening task, I designed an arm gripper system, and I designed 4 options. I decided on using the linear lift. In my original design, I had it so that the drone would land, and then the arm would extend up and clamp. However, after doing a multitude of experiments, I found that this design messed with the center of gravity of the drone too much, and the drone could not handle it. So, After a couple days of indecision and brainstorming, I came up with a unique out-of-the-side-box solution for this problem. My solution was that the drone would fly up to the doorknob and then clamp. Then, the drone would slowly land and provide support. This idea was truly genius because it solved the two issues that I was encountering. First, it solved the center of gravity issue because the arm was staying close to the aircraft until it got mounted. And it solved the second problem of providing support because the selfie stick would come down as the drone landed. For the gripper, I designed 3 different options. And finally, I decided on the 2-finger parallel gripper. To complete the auto-injection task, I designed 4 different auto-injection systems and decided on the modified linear lift one, for it is strong and easy to assemble, although it is a bit heavy and the string has a potential tangle risk. To complete the emergency medication pillbox task, I designed a medication box that was mounted at the front of the drone beside the injector. Before I start prototyping, for the mechanical design part, I used SolidWorks to complete all 3D models and assemblies. Then, to show the simulation for each system. For electrical design, I used Tinkercad to create my schematic and make sure that my electrical flow was correct. When I put it together, it would not fry any of my circuits. After I realized that this drone did not have a high enough payload capacity, I had to buy another drone. In order to minimize costs, I was able to use existing parts and resources effectively. For example, I was able to incorporate my mom's old selfie stick into parts of my arm design. I was also able to borrow one of my dad's pumps in order to test my design idea. I also used my sister's floss kit as the emergency medication pill container because it is the perfect shape and the perfect size. It worked for testing, but it kept slipping no matter what materials I switched to increase friction. So, I designed a cap on the top of the hand to stop it from slipping. When making the pulley system for the injection system, I had to use my dad's fishing string to replace the nylon string. This is because the original nylon string was too thick for the smaller pulley. When creating the pulley, I tried to 3D print it, but the material made the shaft hole smaller, which meant that the motor shaft could not fit into this pulley. To solve this, I remodeled the pulley and increased the hole diameter. After this change, I re-3D printed it. Now, the motor shaft fits in easily. During a test where we put a full assembly onto the drone, we found that the center of gravity was messed up. This is because the center of gravity of the assembly on top was not equal to the center of gravity of the one of the drone. This meant that when it took off, the drone became very unstable, and when it landed, it broke off a propeller. Finally, when I finished all the hardware parts I needed for this project, I shifted my focus onto the electrical engineering. This part was particularly challenging for me because I had never wired an Arduino or coded in a C language. So it took me many hours just for troubleshooting. For example, it took me about a day or so to realize that my circuit was not working because my battery voltage was too low. After I switched from a 4.5 volt battery to a 9 volt battery, my problems with the circuit was fixed. At this point in the innovation, we have had 3 valid designs. The first being an auto-injection delivery system. The second being an emergency medical pill delivery system. And these 2 designs have both been fully tested and proven to be successful. We have also had the gripper and arm. Because of limited resources and a short time frame, I was not able to fully test the capabilities of this design. During my research, I found that there are a few medical drones addressing cardiac arrest by delivering emergency equipment such as AEDs to community bystanders in cities. None of them have an automated injection system that can inject emergency medication under live surveillance or open doors to locate patients. In the future, there are many different things that I would like to do with my innovation to improve it. First, I would like to expand my drone to high-risk patients, such as people with diabetes that undergo diabetic comas. 2, I want to increase the efficiency of some of my parts, especially the arm and the gripper. 3. I want to make my assembly smaller and more lightweight. And lastly, I want to reach out to the Heart and Stroke Foundation and the Alberta Health Services EMS for possible collaborations. As of this point, this innovation has won the $750 National Rising Youth Community Service grant for addressing and solving problem in the community. This innovation was also supported by the Robotics Team 10015, Queen Elizabeth High School, Skulk UAV for tech mentorship and fabrication. Currently, I am discussing with the Stroke Robotics and Recovery Lab to refine my design and take my innovation to the next stage of development. Big thanks to all the medical professionals, engineers, and school teachers who have supported me throughout this innovation. Thank you, judges, and thank you all who have helped me with this project.